episode 118, Sextuplet Symphony. And welcome back to another edition of the Syzygy podcast. My name is Chris Stewart, sitting as usual in the office of Dr. Emily Brunsden. Emily, how are you?
Hello. Yes, I'm well, thank you.
Good. Today we are going to be talking about something which came across our social media feeds a little while ago, a couple of weeks ago, which was really cool. We're going to be talking about some awesome exoplanet-related fun and shenanigans today. But before we get onto that, we have not one, but two updates to give on recent stuff. So the first one, Emily, do you remember there was a sample return mission a while ago?
Osiris-Rex.
That's what it was. And remind us, what was the status and what was the point of that one? What happened there?
So this is sample return, one of the first successful sample return mission that we've had. It's very straightforward. It's go to asteroid, get stuff, bring it back. Let's look at it in our labs, which are much easier than taking our labs to asteroid.
Yeah. The hard part is, of course, grabbing the stuff and then getting it back to Earth again. Because, getting to an asteroid and getting samples is hard enough. But then turning around and bringing it back again and getting it safely down to Earth, this is not trivial stuff. This is not easy. But they managed it. Yeah. Right? And this we did an episode about this, I don't know how many months ago, several months ago, certainly last year, right? And then we did an update, which was, great, we've got the sample container back. And this is a really locked up container, right? They really had to go to town on, we don't want this contaminated as it's coming down, hitting the ground, rolling around in the dirt. We need to keep the samples from the asteroid really, really secure and contained and quarantined.
So much like a pharaoh's tomb, there was kind of an outer chamber and an inner chamber.
Yeah, right? And there was a problem.
You see what I did there?
I do. See what you did there. But there was a problem.
Yes.
And the problem was they couldn't get into it.
Well, yeah, they could get into the outer parts, and they got little samples from the outer parts, which have a low risk of contamination, but higher risk of contamination than the inner parts. I think there were 35 kind of nuts to hold the whole thing together. And it's not just like you can sort of grab a spanner and undo it in the desert and see what's inside.
It's not like you just don't happen to have the right Allen key. This was complicated stuff, and they really struggled to get into this thing.
Yeah, because you've got to do it in full clean environment, right? You're not just walking up to it with your tool. You're wearing it in the box with the glovey suit things, and it's all depressurized and decontaminated, and yeah.
Yeah, and to be clear, they had thought about this. It wasn't like it just landed back on Earth and they went, we didn't think about that. How are we going to get it? Don't you have the spanner? I thought you had the spanner. No, they clearly thought about this, but it took a lot longer, I think, than most people thought.
Yeah, some of them were a bit jammed.
Yeah. So the important thing is, just this week, it's been announced they finally got into it.
It's open.
There was a picture going around, and it should be showing up on the chapter art right now of the inside, the material that they actually collected from the asteroid. They're finally in, which means they can start doing some science on it and sending it around all over the world for other people to do science on it to get some really cool information about this asteroid.
Do their swapsies, right?
Yeah. So that's cool. So that's update number one. Well done for actually getting into the sealed pharaoh's tomb of this asteroidal stuff. That's number one. Number two is just last episode. Emily, can you remember back to episode 117?
I remember it clearly.
Can you remember where we got to at the end of episode 1? Just give us a little summary update.
Yes, so we had JAXA, the Japanese Space Agency, were landing SLIM, the smart lander, onto the moon. So this is really a high-precision exercise, and can we land at a really well-defined, within 100 meters of a particular spot
Yeah, they call it the moon sniper, which is quite funny.
Had a couple of little rovers on board as well. This was almost all technological tests more than scientific experiments. But of course, the science will come once you've developed the technology to do it, right? So where we got to was we watched the landing live. We could see it on the little screen. We could see the animation of the lander coming down, 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 down.
Yeah, we were watching live on YouTube, and it was very exciting.
It was very exciting.
Yeah.
And then it touched down, and we went, hey! And everyone at JAXA went,
very quiet.
oh.
and there were lots of reports or lots of statements like, we are just waiting for confirmation, and we're just checking the status of the lander, and long pauses, and filling of gaps with music and chatter, and what's going on? And by the end of the episode, where were we?
So we were at the point where we assumed it landed, but it wasn't clear if it had safely landed, if it had landed in the intended orientation, if
was there
the
just
rovers had deployed.
Smoking crater where it was supposed to be. I mean, it seemed like there were statements like telemetry says it has landed, but was there information coming back that said everything was okay? It was unclear. And when we hit the stop record button here in Syzygy HQ was when on the live stream from JAXA, they said, don't go away. We're going to be back soon with a press conference. And that always, I don't know. It feels to me like, oh, that's not good. It's not good if we're going to get an update via managed press conference. So
I think it was fair to say we were concerned.
Yeah, that's where we got to. So here's a little update on what's happened since then. That press conference, they announced we have landed successfully on the moon, with a big asterisk on it. And just prior to the press conference, I'd seen going around on the social medias, on what used to be known as Twitter and other things like that people, you could go and have a look at some of the deep space network. These are the big telescopes that they got pointing out into space to communicate with spacecraft that are out there, including things on the moon, right? And this worldwide network of telescopes sending and receiving data to these things. And you could see SLIM and LEV-1, which was the little hopper rover, which was ejected. I think they said it was about 2 meters up that they spat these LEV-1 and LEV-2 out onto the moon. And both SLIM and LEV-1, like LEV-1 is this tiny little thing. It's only like 2 kilos or something. But they were both communicating back to Earth. And it's like, okay, well, something's happening.
Yeah,
like it's not a smoking crater. So this is good. But what does it mean? There's no images, nothing. And at the press conference, they said, we have landed. It's been successful. However, what seemed to have happened, people have sort of pieced it together, is that when this thing landed, they deliberately landed it on a slope. And part of the landing procedure was it would kind of come in kind of sideways, hit its back legs and tilt forward and rock forward into its final resting position. And that may have gone a bit too far. It may have sort of tumbled or gone in the wrong direction. And that meant that its solar panels weren't pointing at the sun, which is not good. And so they only had a couple of hours of battery in order to, okay, quick, just send us some data, do some checks, and then shut down before you're forced to by dead battery, which we may not be able to revive. And we just got to wait for the sun to move across the lunar sky. And it took me a minute to realize that's different to the sun going across the Earth's sky, right?
Yes.
The sun going across so just explain that for a second, Emily. Why is the sun going across the lunar sky different?
So I think it's easiest to imagine a day on the moon. So on the Earth, we have a 24-hour-ish day because that's how long the Earth takes to rotate on its axis as it's going around the sun. Now, of course, the Earth moves a little bit more in its orbit as it goes around the sun, but it's marginal compared to how far it goes and it's on its own axis. The moon, however, has a orbital period. So the time it takes to go around the Earth is about 30 days, right? A lunar month. Its rotation period is also around about 30 days. Because this tidal locking, that's why we always see the same side of the moon pointing towards us.
Right.
So if you step back and imagine looking at the moon, forget about the Earth, just think about the moon rotating with respect to the sun, then a day is about 30 days, 30 Earth days long. One moon day is about 30 Earth days long.
Yes, I mean, when the moon is in the sky, like if it's a full moon, the next night it's almost a full moon. And what you kind of forget down here on Earth, because we see the moon go across the sky and then it's gone. What you forget is, but at the moon, like that's basically full moon that entire time, like that sort of midday sun, that entire time. And it takes half a month, basically, for daylight to sweep across the surface of the moon. And then it's in darkness or, increasing darkness for the other half of the month. And you just kind of forget that. And so when the solar panels are pointing in the wrong direction on our slim lander, that could take a while for the sun to come across into the right part of the sky. It's not a couple of hours. This could be days.
Yeah. And at least with the first announcement, it wasn't clear what angle those solar panels were at. So even if they were kind of almost sort of stood upright in the lunar surface, if you imagine that, it could take quite a while for the sun a few days for it to come round and be able to sort of strike those panels from the right angle to illuminate them.
So that's where we are. So that was the news as of just after we finished recording. Today, JAXA has put out a couple of press releases. First of all, just confirming, we've had communication with SLIM and with LEV-1, which is in itself staggering. As I said a minute ago, like LEV-1, this tiny little hopper rover thing that springs its way around, it has sprung, right? It popped out, hit the ground, and they've sprung it around a couple of times, which is cool. And it has been itself directly communicating back with Earth, which is the smallest thing we've ever put on the moon that can directly communicate back with Earth. So that is really cool from a technology point of view.
Very, very cool.
That's all working. LEV-2, the little transformer rolly-wheelie thing, also worked. What we haven't had is any images from that yet. It has a little camera that pops out, and it's unclear as to why. And they're not being particularly vocal about that. Just we're working on it. Is basically what they're saying.
But it does rely on relay from SLIM. That rover. So it could be related to SLIM rather than the rover itself. Yeah.
Everything may be working fine, and we just have to wait until we've got more battery power. But the other press release was we do actually have a couple of images. A couple of images have come through from SLIM itself. Not great images, but images. And you can see the lunar landscape out away from the lander itself. And what they've gone and done is, in order to try to get some sense of what are we looking at? What's the range that we're looking at? You're looking out across a landscape. So they're basically gone and go, okay, there's a bunch of big rocks here. Let's put circles around those and give them nicknames so that when we refer back to this, we can easily communicate. Okay, so that seems to be like maybe a meter across, and that one over there, maybe that's 5 meters across. And they've given them all nicknames, and they're all dogs. They're all breeds of dog, which I think is kind of fun. So anyway, that's where we're up to with SLIM.
Yep.
It's working with an asterisk, and we'll see what happens when the sun comes across as to how much it's working and how much they can continue to operate on the moon. But to all intents and purposes, the technology worked as planned. Yeah,
I would say the number one mission goal, which is can we land this thing precisely and where we want it to be, absolutely a success.
Yeah. So huge cheers to the Japanese Space Agency, JAXA. Yeah. Well done, everyone who's worked on this thing, especially the little transformer rovers, because they're cool.
They're very cool.
I did look it up. You can buy the little ones, and if anyone wants to buy us one, links in the show notes. But look, that's not what we're here to talk about today. That's just a very long-winded update on a couple of past episodes. Today, Emily, we want to talk about exoplanets that are making music. What's going on here? Bring me up to speed. What's happening?
Particularly, we want to talk about HD 110067.
That's what I was going to say.
Yeah. It's becoming famous, actually, in its own. There are particular catalogue numbers that do kind of get ingrained in your mind, and this one's definitely one of them.
This is an astronomical household name.
Indeed. So this is the star, and this star hosts what we call a resonant chain sextuplet.
Resonant chain sextuplet. Okay, well, there's a bit of unpacking we have to do here. So first of all, who's announced this? Where is this information coming from?
Yeah, so we're really talking about research that was published in early December, late November last year,
2023.
Yeah, so I think the paper came out on the 29th of November. So that was Raphael Luke, who was in Chicago, and a whole bunch of other collaborators were looking at light curves from TESS and other also supplementary data to look at this particular planetary system. In this system, so we've got the star, which is the HD number I just gave you. You've got 6 what we call sub-Neptunian planets.
So sub-Neptunian, smaller than Neptune.
Yep.
Is that important in the scheme of things, or is that just giving us the sign?
It's important, and we'll come back to that. But the interesting thing is with these 6 planets, so super Earth, sub-Neptunian, whatever, these planets are in a resonant chain. So that we know about resonance, we know about orbital resonance. I just gave you an example in the intro, right?
Yeah, we have a
tidal locking
resonant
of
chain of the Earth and the Moon.
Yeah. I mean, it's not a particually. Well, it's not.
I guess
it's not a resonance chain. It's a locking, but it's due to the same tidal gravitational forces. But a resonance formally is where you have a mapping of the periods of 2 objects. So in this case, let's take the first 2 planets, inner planets. Planet 1 in the system is going around, and every time when that planet goes around 3 times, the second planet out goes exactly around 2 times.
Right. So that's a mathematical link. And that's not coincidence.
No. So these resonances are set up basically by the orbital dynamics. They're kind of a low point of where everything eventually gets to in terms of these systems, and we'll talk about a bit more about that. But what's exciting is you got this resonance, not just of 2 planets in the system, all 6
of them
are in resonance.
I mean, I can completely see how you'd get a couple of them, maybe 3, but by the time you get to 6, like that just feels mathematically really unlikely when you figure out everything that's going on. But here we are.
Yeah, and the link, of course, to music is then where you're talking about things like harmonics. So a harmonic is when, say, you've got a string and you pluck a string. There's lots of different ways that string can resonate. And it can resonate with, say, a 1 node or 0. Your 2 ends are sort of fixed, and then you've got an antinode that can wiggle. So it's the very simplest thing you can do.
You pluck a guitar string, that's the note that you get. Is basically almost entirely that fundamental first harmonic.
Yeah. And then the first harmonic is the one where you go into
that fundamental mode.
Fundamental mode. That's right. Yeah, and then your first harmonic is you put your finger bang in the middle to create a third node, a third point that doesn't move, and then your other 2 bits that are now halfway between all your nodes, they will wiggle instead.
Yeah. So any stringed instrument players out there, you will know this, right? You can play harmonics on a guitar or any other similar instrument by just touching your finger in the middle or a third the way along or a quarter the way along, and you can get these different resonances, these different harmonics of the string.
Yeah.
And so there's a similar kind of effect coming into the orbital periods here.
Yeah. So what you can do is map that onto a sound. So you can say, well, this what we call 3-2 resonance, you can make that a sound.
Sure.
And then if you take in the next planet in, you can make a sound when that planet comes into resonance. We've got a really nice visualization that we can, I think, put in the show notes and so on.
There's a lovely video that they've put out of this.
And what they do is they basically say, well, let's imagine there's a 0 point. So draw a straight line coming out from the star, and you start all your planets going on from that 0 point, and then when they line up radially from the star, then you make a noise.
Yeah.
And
so it starts off this lovely video, which we have linked in the show notes, and we'll put in some of the audio in it. Just have a little listen. It's really nice. Yeah, it's a really lovely way to
audibly describe, I think. Yeah. I think that's the word.
Audibly, I think is
audibly describe, yes. What's going on. Because I often think in some ways we're a bit ridiculous doing this podcast, aren't we? Because astronomy is such a visual field.
What are we even doing?
Yeah,
it's ridiculous.
It's full of pictures, and we're always talking about how glorious things look. But so it's really refreshing to come along and say, well, doesn't that just sound amazing? It's a whole new sense. It's a whole new way of interacting with the universe.
Yeah, well, it's something that you can do in this particular case, which it doesn't just sort of replace the visual. It's a completely different way of conceptualizing what's going on. You know, we hear these kinds of relationships. We don't typically see them. We hear this, and so that's how you can make sense of it, at least to some degree. And beyond that, it is beautiful in a different way. It's just with that different sense. It's fabulous.
Yeah, because if you took any system, even if you took the solar system, right, and the planets that we had, and you tried this exercise, it wouldn't sound good.
No.
Because you wouldn't be playing notes.
Well,
right?
this is what I was going to ask you. So how special is this system? I mean, what you've said is, here is a star. Where is this star, by the way?
It's a relatively close star. You can tell that in a few ways. If you're really nerdy, you can tell it because it's got an HD number, which
right. Well,
it's fairly bright.
That one passed me by.
But it's about 105 light years away, which is not too relatively close.
Sure.
Yeah, it's not in our local neighborhood, but it's not ridiculous.
And presumably most of the, if not all of the planets that we're studying, all of the stars that we're studying, exoplanets, are actually, none of them are terribly far away.
That's not quite the case, actually. Okay. Often they are very far away. For example, Kepler was very good at discovering planets that were very far away.
Right. Okay, I stand corrected. But this one's reasonably
this one's
close.
Quite close.
So we've got a star. It's got 6 planets, and we've known that for a while. Presumably, this is not a brand new discovery.
Well, we knew about 2 of them. So the extra 4 and the resonances of all the 6 are new.
Okay.
Yeah.
But just the idea of having 6 planets, which are in this really interesting, resonant chain, as you called it, like there's mathematical relationships between these different orbits. How common is that? Because I don't think, other than perhaps our moon and maybe presumably some of the other moons, I know Mercury is in an interesting resonance in its orbit around the sun.
Yeah.
But are there other relationships like this in our solar system?
Not really. There's not many. So the way you get these resonances isn't by chance. It isn't just you build 100 solar systems and you hope one randomly has this setup. So what happened? Well, we're going to come back to, I think, the building part, but at least what you expect to see out there in the Milky Way and the stars and planets that we see, you only find these resonances in systems that are very, very old. Okay. Well, they have to be two things. They have to be quite old, and they have to be planets that are quite close to their host stars. And there's one reason, which is actually behind both of those. It's the gravitational influence. So you need really strong gravitational influence because this is the ultimate driver towards resonance. Even if you start off your planets in any configuration that you can think of that they may have been born in or that they may have migrated to in their history, gravity eventually wants to pull things into these resonances as you lose energy through friction, through tidal forces.
Right. So it's a little bit like the resonance position, the resonance situation is, in a sense, kind of like the lowest energy state of this. And you could have it in pretty much any other orbit you care to think of, but over long periods of time, the forces on the planet which are slowing it down, which are causing that orbit to change slightly, it's going to nudge it just slightly over really long periods of time towards one of these resonances. Bit of drag here, bit of a pull from something else there will generally shift it towards a resonance.
Yeah.
And so if you wait long enough, that's where they'll be. Yeah.
So you got to be close to your host star, so you have lots of gravity, and you got to wait for a long time so that that gravity can very slowly do its magic and draw out the energy and settle down the planets into these orbits.
Right. And so that's why you need really old systems and systems with the planets nice and close. So you've got that strong gravity over a long period of time.
Yeah.
So our solar system, it's too young and too spread out?
Exactly.
Right.
Yeah. Yeah. So that's why it's only Mercury that's on its way to this kind of tidal locking resonance position. It's the closest planet to the sun, so it's got that much stronger gravitational.
And remind
force.
us what's the resonance with Mercury? What does it do that's special?
It's getting into a spin orbit resonance. So I think it's 3-2. The how many times it rotates on its axis to how many times it goes around the sun.
Right. Yeah,
so it's kind of an internal resonance.
Days and years for Mercury are weird.
Yeah. But we've seen lots of other examples of exoplanets, including we suspect, for example, we don't actually have a measurement of this, but it's highly suspected that the TRAPPIST planets, some of the most famous exoplanets, TRAPPIST-1 system, those are likely to be tidally locked to their host star for a similar reason. So that means that much like the moon is tidally locked to the Earth, so it always has the same half pointing towards the Earth, these TRAPPIST-1 planets, we expect they are tidally locked to their host star.
Right. So that wouldn't necessarily show up in the orbital periods as they are for this star that we're talking about. But these kinds of resonances can show up in other ways.
Yes.
Okay.
Yeah. So there's kind of quite a complex set of dynamics, but it's all heading towards the same point, which is effectively what we're seeing in this system.
Have we seen this sort of thing before?
A few cases. So we expect that maybe 1% of all planetary systems in the galaxy might be in some kind of resonance. But then to find all of your planets in the system like this, I think is quite special.
That is really, really cool. And, just to be able to listen to that, as we said before, the audio side of it, just really in a way which you wouldn't get for the tidally locked. The planets are always pointing towards the star and so on. Like, that's cool, that's interesting, but the music of this one is the one that absolutely blows me away. It's really, really cool. I think I might have found us another bit of theme music for the Syzygy podcast. Might have to work that one in there. We'll see.
Excellent. Yeah, so I think it'd be quite nice if we can dig into the system. Let's really get into the detail of what it looks like and what we know about it.
Have a poke around.
So all systems, I think, start with a star, because not only do I think stars are exciting and interesting, but actually everything that goes on in planets is related to their host star, right? So this star, this HD 110067, it's an incredibly interesting star in its own right. It's a member of a triple, so there's 3 stars linked together. 2 of them are quite a relatively close binary pair, so there's 2 going around each other, and then this one is kind of slightly detached.
I'm guessing it would need to be reasonably far away from the other 2, simply because being too close to 2 other stars might kind of upset your planetary systems.
Well, indeed, yeah. There's still a lot of questions about close binaries and planets, and can you make stable planets go around close binaries and so on, which TBD, I think, to look at.
Watch this space.
Yeah. So that's interesting in its own. That it in itself is in a multi-system. It's what we call a K05.
Right, which means what?
Or K0V. So K0 means that it's a very cool star. So spectral classification K, it's on the 0th rung of the K class. Very, very cool star. So it was born with a low mass compared to the sun. And therefore the surface temperature is much lower than the sun. Estimate maybe around 3,900, 4,000 Kelvin.
And the sun is what?
Around about 6,000.
6.5, something like that?
Yeah. So it's about 80% the size of the sun as well. So it's a littler star, right? Now that's, I guess, good, because if you're going to snuggle your planets in very close to a star, you don't want it to be too hot.
Don't want it to be too hot and big. That would be nasty.
But that being said, all these planets are actually well inside the orbit of Mercury in our own solar system.
Oh, wow. All 6 of them?
All 6 of them.
Wow.
So I think they range from, so I'm going to use astronomical units here, which is the distance between the Earth and the Sun as the reference. The closest one is 0.08.
0.08, like less Like that's 8%.
8% of and
Wow.
then the furthest one's about 0.26.
Because
so about a quarter.
What's Mercury in AU? Is it about a third? Have I got that right?
I can't remember off the top of my head.
Wow.
3.4 or something like that, yeah.
That's insane.
Yeah.
Okay.
Yeah.
These are really close.
They are really close. So they're all inside Mercury's orbit when mapped onto our solar system. And they're all big. I think we mentioned before, they're all these sub-Neptunian. This seems to be the phrase that's settling in the field, sub-Neptunes.
Right.
There were lots of options we could have gone with. We could have gone with super Earths. We could have gone with something. Sub-Neptunes seem to be settling.
But I mean, just to be clear, like Neptune's not small.
No.
It's not like a small thing. Like sub-Neptune, there's a lot of things which are sub-Neptune. I'm sub-Neptune.
Well, indeed.
So how small can you be and be sub-Neptune?
Well, the size of the Earth, basically.
Okay, right, all right.
Yeah.
Right.
So it all stems from the weird quirk of our own solar system that we've noticed that in our solar system, if you were to line up the planets in order of size, then it goes from the Earth at one Earth mass all the way up to Neptune, which is a 10-ish Earth masses, something like that. And so there's this massive gap. And I mean, before we found other planets and other solar systems, we didn't know, is that just because you can't make planets that are that size?
We don't have any, but does that mean anything? Or
did we just not get any because they're very difficult to make? Or what? Are we just weird?
Yeah.
Turns out,
with eight planets, that's not a big statistical set.
Well,
so,
no. It turns out it really is that we're weird.
Okay.
Our solar system seems to be very strange. Actually, these are some of the most common types of exoplanets that we've found. And when you do all the debiasing and figure out what actually the population is of exoplanets in our galaxy, we should, by all means, we should have these. More than half of stars that are like the sun have these kinds of what we now call sub-Neptunian planets.
Right. So, I mean, that really does then lead you to the question, which is why don't we? But maybe that's a podcast for another time.
Yeah,
I have a feeling we've talked about this before.
A little bit, yeah.
Buried way back in the back catalogue.
Yeah. We don't know all the answers is the short answer.
We
but
just don't.
Yeah, we
okay.
don't.
But this one does.
Well, it's got 6 of them.
6 of them. What are the odds?
It's
Pretty high,
overcompensating, perhaps.
Yeah.
So there.
Has anyone looked inside the orbit of Mercury? Like there might be dozens of them in there that we've just never. Oh, those. Oh, we never noticed those before. No.
Well, we might have one. To be fair, if you really want to be very technical, we might have one. This Planet 9.
Oh, so not inside. I thought you were about to tell me there might be a planet between Mercury and the Sun. I was like, what? No. You're talking way out there. Yeah. Okay.
So far out, it's very difficult to find. So
yes, it could be.
Maybe. But we don't know. But certainly no, not inside the orbit of Mercury.
We would have noticed that.
We would have noticed something. So these planets are ranging from roughly 3.9 times the mass of Earth up to 8.5 times the mass of Earth. So they're fairly large things. And what's quite interesting is that because we've been able to measure when the detection method of these has come from transit measurements. So this means that when we were looking at the host star, actually with TESS in this case, we saw the light dim a little bit because the planet moved in between us and the host star.
Mm-hmm. That's how that works.
And that gives us a direct radius measurement for the planet, right?
Oh, by the amount of dimming.
Yeah.
Oh, okay.
Yeah, so you can figure out what your radius is of your planet.
It's not just that it's there, we can actually figure out this is how big it is.
Yeah.
That's wild.
Yeah. And then we get the mass we've managed to get some what we call radial velocity measurements. So this is where we look at the light from the star itself is wobbling a little bit, and sometimes it wobbles a little bit towards us and sometimes it wobbles a little bit away from us because of the gravitational tug of the planets. You can measure that wobble by the change in light going from blue to red.
Right, because it's coming towards or away.
Yeah. And because that whole process is driven by the mass of the planet, you can figure out the mass of the planet.
And presumably that's much more pronounced because the star itself is quite small.
Yeah.
And so a reasonable sized planet's going to give it more of a noticeable tug.
And they're nice and close as well.
Yeah.
So it's been very successful and been able to get the masses of the planets from these radial velocity measurements, the radiuses of the planets from the transits, put those together.
Size and mass, radius and mass, put them together, you know your density.
You know
density. how dense these things are.
And that's very exciting because then you can say, is it rocky?
Right.
Is it liquidy?
Yes.
Is it gassy?
What is it? What's it made of? Cool.
Very cool. Now, this is we must be honest, this is a density we call the bulk density, which means it's the whole thing.
Yes.
Right?
Yeah.
So the Earth has mostly rock, but we've got a bit of atmosphere, right? We've got other planets that are very little solid and mostly gas in our solar system.
Yeah.
We can't tell the proportions between how much rock, how much liquid, how much gas.
But you can get the average of all of those. And I'm guessing that the average for a very gaseous planet like a Jupiter-y, Neptune-y type thing is very different in density, in average density, to a mostly lumpy, rocky thing like an Earth or a Mars.
Yeah, exactly. And it all depends on temperature, because as we know, especially with gases, then they change density with temperatures. But when you put all that in and put it all together, then you can see that these sub-Neptunes, these 6 planets, are all pretty much the same, and that they've all got a very significant hydrogen probably dominated atmosphere.
Right.
We say hydrogen probably because it's the lightest element. So they've got a very light, big light atmosphere.
But when you say atmosphere, do you mean like composition generally?
Yeah.
Right.
Yeah.
Okay.
Yeah. So they've got probably some kind of rocky, densy core that the atmosphere's clinging onto, basically. Right. But a significant fraction of the planet is gassy.
Right. Okay. That's a heck of a lot of information that we've been able to get from watching the blinking and wobbling of a distant star.
It's amazing.
It's quite extraordinary.
Yeah. And what's so exciting is, so we've got atmosphere, likely very strong atmosphere. It's a very close system, super cool. We've already talked about the fact that we detected these via transiting.
Yes.
So that's very, very cool, because when you put this all together, this system turns out to be the closest planetary system to us that has 4 or more, I think, planets. It's a record holder now in its own right. Anyway.
And that's interesting in and of itself.
So now we've got 6 gassy planets that are transiting, that are nice and close, and we've got a really large exoplanet atmosphere observing space telescope that has just been waiting for this opportunity.
I'm guessing that there's probably going to be a little bit of time booked on that telescope.
It's probably already pointing that way. I'll be honest with you. I haven't looked at the queue scheduling, but yeah, this is the prime target for James Webb. This is exactly what James Webb was designed to do.
So what sort of things would the James Webb Space Telescope, we hope, be able to tell us by pointing at this system? So
what James Webb is set up to do with exoplanet atmospheres is when that exoplanet moves in front of the host star, which we know it does, the light, so we have the light coming from the star, and we can measure all that, and we can measure the chemical composition of the star by breaking down the light into its constituent wavelengths and learn lots about the star itself. But when the planet moves in front, some of that light, if its planet's got an atmosphere, some of that light travels through the atmosphere before it gets to us.
Yeah. Yeah, like literally through it and straight on out the other side.
Yeah. Yeah. And that changes the light, right? If you've got hydrogen in the atmosphere of this planet, that hydrogen is going to absorb some of the light that's coming from the star. So you're going to see a different spectrum, a different set of chemical elements when the planet's in front of the star as to when it's not. When the planet comes around in front, it'll leave its fingerprint of the chemicals that are in its atmosphere on the light coming from the star. You'll be able to look at it and go, well, hang on, that changed. That means there's hydrogen and nitrogen and whatever in the atmosphere of this planet, which is cool. It's cool. It's incredibly hard to do. Yeah. It's really not easy. It doesn't sound easy. No. So you need to have, first of all, really nice flash big telescopes sitting out there. Which we do, James Webb, looking at you. But you need these bright stars and close systems so that you can get a lot of, signal, basically, to be able to do this kind of work. So it's just made for James Webb. When you were saying before it's not particularly bright, or did I get that wrong? Yeah. It's bright because it's near? Yeah, right. Yeah. So there's 2 reasons why a star can be bright. It can be bright because it's intrinsically bright, or bright because it's quite close to us. Right. Either way, as long as you're getting enough light to get a decent signal,
James Webb should be able to do something with it.
Yes.
Yeah.
Yes. And this is a really good system to be doing that with. And a system with these planets that we have so little information on because we don't have one.
Yeah. I do know that recently there have been some headlines about we've found signatures of potentially life-related molecules in the atmosphere of a distant planet. Like I remember that coming up in the last couple of months, and I'm assuming it was probably JWST, and I'm assuming what they were talking about was, we've seen some sort of organic chemistry coming through in these atmospheres, and organic chemistry makes it sound like life until you talk to an organic chemist and it's like, no, that's just chemistry involving carbon. Don't get too excited. This is not life that we've seen here. But it does kind of lead one on to that question of, could JWST like spot signs of life on other planets? I'm guessing that's a moot point in this case because we've got 6 planets that close to a star and they're all Neptune-y type planets or sub-Neptune planets. There's not going to be any life on these things. I think we can probably put a big box around that.
Well, what we've almost deliberately, but not actually deliberately, avoided saying is that these are none of these planets are in the habitable zone.
Right. Yeah, that's reasonably clear.
Yeah. So they're all too hot.
Even near a fairly small cool star, that's really close.
Indeed.
Yeah.
So I think the temperatures are around, the mean equilibrium sort of temperatures of these planets are at least 180 degrees Celsius, probably up to 500 degrees Celsius.
Mm-hmm.
It's a bit too hot.
Yeah, not particularly conducive. I mean, look, we find life in all sorts of places on this planet. Crazy little microbes and things, but I'm not going to start putting a cheeky 50 on JWST spotting life around any of these planets anytime soon.
No. And what we always need to keep in the back of our minds is a little bit of cynicism when it comes to life in exoplanet atmospheres. We're very, very good at detecting what these chemicals, molecules, etc. are in the atmospheres. What we haven't got a very clear idea on is what actually is a signature of life.
Yeah, that's a much more complicated.
Yeah, there's no simple answer.
question.
You can't just say, hey, there's methane, therefore there's cows,
Yeah, it doesn't work that way.
No.
Turns out methane comes from other places too.
Yeah,
than cows.
There's no single element or molecule that you can't find a pathway to generation without having, in an inorganic sense, without life.
Mm.
So how do you say that there's absolutely 100% life there?
It's why
it's
these,
not easy.
It's why these headlines just do make me laugh. As soon as an astronomer comes out with, we've found organic molecules, wait for it in 3, 2, 1. Out come the breathless headlines of, we've found signs of life. No, we haven't.
Well, it's the penguins on Venus thing again,
right? Yeah, exactly. Like we haven't. We just haven't.
No.
Okay.
And it's not to say we're not working really hard to figure out what we call biosignatures are.
Sure.
And there's lots of options to explore, and it's probably what we end up sort of settling on is some kind of ratio, an imbalance in particular levels of particular molecules. But exactly what that is still hard to pin down.
Well, and I guess the other point would be that it would never be any one signature. You'd find something and you'd go, that seems off the charts. And so first of all, you'd try really hard to confirm that that's right. Like we found this signature which seems like the sort of thing that you might expect life to do. And you'd check that really, really hard. But then you'd also go, well, there might be other ways that could come about. It could just be coincidence or it could be some other mechanism we're not thinking of. So is there anything else about this atmosphere that makes us also think, well, that's kind of weird? And you just keep investigating. At no point would you say, we found molecule X or even molecule X in ratio to molecule Y, therefore life. You need more than that.
Oh, yeah.
Anyway, getting
it's
way
the biggest claim I think you could ever make in science. So you double check what you
double, triple, quadruple check, and then go for a walk around the block and take some deep breaths. But yeah, look, none of that is the point of any of this. I just figured I'd raise it because I'd seen those headlines not too long ago, and we were talking about atmospheres and so on.
Yeah, but yeah, life is definitely off the table for this system.
Yep.
But that doesn't mean it's not interesting.
No. So Emily, we've just in wrapping all this up, right? We've found we got a star. We initially knew it did have 2 planets going around it, but now we know there's 6. And It's not very far away, so we can have a really good hard look at it. And the really cool thing is that we found that there are 6 planets which are winging their way around this star really close, like all of them within the orbit of Mercury, which is bananas. But not only that, they are in these crazy linked mathematically resonances, this resonance chain. Can you like give us a sense of like what, you were talking before about the guitar strings and how you can have, certain, the fundamental vibration and the different harmonics and so on. And that's a very clear mathematical relationship, right? That's simple. I'm guessing this isn't quite as simple. So can you tell us about the numbers?
Yeah, it's not actually that far off being very simple.
Okay.
It's one of the simplest sort of chains you can set up, which is interesting in its own way. So to preface this, let's remember that when we talk about what our nomenclature is when we talk about exoplanets.
Okay.
We'd have the way we name exoplanets.
Oh, that's right.
Isn't that we start with Bill and Jude? We start with the star name, HD110067, and then we give them letters, lowercase letters. For reasons we're still not completely clear on, we skip A.
Right. Yeah.
So in this system, we've got planets B, C, D, E, F, and G.
Good.
Yep. So I'm going to use those when we're talking about them. So as prefaced, I think just before, we talked about how resonance, it means that for every C goes around twice and B goes around 3 times.
Okay.
Or B goes around 3 times, C goes around twice.
That's
and then
the kind
they
of
meet
relationship
again.
we're talking about. Yeah.
Yep. And then they meet again. Now, if you take C goes around 3 times and D goes around twice.
So it's, hang on, if we start with C, the second planet out, because C is the third letter of the alphabet, the second planet out, it goes around 3 times for every 2 times that the first planet goes around.
No, other way. So B goes around 3 times, C goes around twice.
C goes around 3 times, D goes around twice.
Correct.
Okay, I'm liking this. Yep.
Yeah. D goes around 3 times.
Let me guess. Yes. E goes around twice?
Exactly.
Get out of town.
And
really?
This is the chain. Yeah, this is the chain. Now, E goes around 4 times.
4 times, just to mix it up a bit. Yep.
F goes around
3 times?
Yep.
Hey!
And F goes around 4 times. G goes around
3 times?
Yeah. So these are
wow. So we're going sort of this 3 to 2 for a while, and then it mixes it up and goes for a 4 to 3.
Yeah.
Wow.
And these are quite fundamental resonances because there's only one number different. So 3 to 2 or 4 to 3, it's it's not 7 to 3 or something weird like that.
That's
right?
wild, and that's why when you listen to it, sort of the audible representation of that's why it does sort of sound a bit musical.
Yeah, and the whole maths of the whole thing, which is I love this bit. The resonance from B, the innermost planet, to G, the outermost planet, is 6 to 1.
Wow. That's wild.
So the whole thing is just all mapped out.
That's so neat. Like I was fully expecting this to be, they're resonances, but it's a kind of a wacky resonance. It's like one of those songs that you listen to and go, what's the time signatures? Oh, this is 14/9. Oh, okay, right. I was expecting it to be kind of weird. But no, this is really
if
simple.
you're musical, you'll know what 3/2 means, right?
Yeah.
And you'll know what 4/3 means, or
even 6/1.
I don't know many songs in 6/1, but
well, no, but I mean, you come across sort of 6/4 and things like that. That's wild.
Cool. And so, if you take all the periods, how long it actually takes, because these planets are whipping around, pretty quickly. I think the fastest one goes around in 9 days.
Wow.
The furthest one out goes around about 55 days.
That's really fast.
But let's say, again, we line them all up on one straight line and you set them off. It will take 492 days exactly, and then they'll be bang in that position again.
492.
Yeah.
Wow.
And then the whole thing will just play. The song will play again, and then bang, you start the song again. Another 492 days later.
That's crazy. That's crazy. When you say day in that sense, do you mean?
I mean Earth days. Yeah.
Earth days. Okay.
We measure all planets, assuming that they're.
that's very Earth-centric of us.
It is very much so. But yeah, and what's exciting is TESS is very good at picking up these planets that are quite close because they're going around at these short periods, right? TESS's duty cycle on a particular star is often only about 28 days or just shy of a month.
Okay.
So, if you want to find planets, you're not going to be finding planets that have periods of years and years and years. but you can find these quick ones. What's interesting is some of these planets weren't actually discovered by directly seeing all the transits. In fact, if you look at a 6-planet system and look at the transits, it's an utter mess, right? Really,
yeah, I mean, how do you know which is which?
Well, exactly.
Like, there's a lot of data there with 6 planets, even if they're in these amazing resonances. You don't know that going into it. It's not like you can go, well, I know that particular blip was that particular planet. All you're seeing is a star with blips. And lots of them.
Exactly. So we knew about the first 2 from 2020 TESS observations, so B and C. And those were quite quick. You can see 9 days, boom, 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 boom,
yeah,
boom.
You'd see a pattern there.
Yeah, that's quite easy to pick out when you're observing in 28-day chunks.
Even I could probably have spotted that.
Yeah, but then you've got these other ones just almost randomly seemingly popping in and out. And if you only have 1 or 2 measurements of them, it's really hard to figure out what the period is, right?
Well, particularly, like you said, TESS is usually only pointing at it for maybe 28 days.
Yeah.
And some of these have considerably longer periods.
Yeah, so
how does that work?
you get a snapshot often with TESS of a 28-day, boof, there's your 28-day piece of data on that star. But then it might be a year, 2 years, 18 months, whatever, until you get another one. And if you've seen transit in sort of data set A and then you've got data set B, which is 2 years later, you don't know what's happened in that meantime, right?
It's very difficult to fill in that gap.
It is.
So how the hell did they do it?
Well, there's a lot of clever maths going on in here. It's very interesting.
Never underestimate a keen astronomer's ability to find patterns. That's wild.
Yeah. So there were 2 planets, I think they called them duos, that they did have 1 transit in each of these 2 separated data sets. But you don't know, of course, how many times it's gone in between those 2.
It could have been once.
That could have been it.
That's the next time. We just got lucky.
So they did figure out, basically, we need to observe this, but we're not just going to waste time by pointing all the telescopes at it and just waiting for it to happen again. We'll say, well, we can rule it out if we get an observation right exactly here. We'll either get it and we'll know that it's there, or we won't, and then we'll know it's another different period.
Gotcha. So you start ruling things out by going, well, have a look at it now. It's not there. Cool. Well, we know that it's not all of these particular resonances then, or it's not any of these periods.
Exactly.
Nice.
Yeah. So that's what they did with CHEOPS, which is ESA's characterizing exoplanet satellite. It's not CubeSat, but it's a sort of a smaller version of TESS.
Okay.
And it's a nice little satellite for looking at planets around nearby stars again.
Right. I guess you use TESS to find the big data in a sense, and then you use CHEOPS to sort of start filling in the gaps.
Yeah.
That's nice. That's clever.
Yeah, so that's what they did, and a lot of interesting maths, and then you ended up predicting basically. 2 of the planets were predicted before they were even spotted. So that was quite exciting. What that leaves us, of course, with the possibility is we've only gone up to this planet 6. There could be more. There could be more with 70-day plus orbits.
Right. That's an open question. We found this many, but who knows?
Yeah.
Could be loads of them.
Exactly. So, is there another 4-3 resonance out to planet H? I had to quickly go through my alphabet there, but so there, at least with the system, you've got a good idea of when to look.
Yes. You don't have to be looking all the time. It would be really weird though, wouldn't it, if you found another planet that wasn't in a resonance anymore? Like the next one out breaks the pattern.
Well, that would be even possibly more exciting, because then you're really starting to dig into how did the system get to where it is today?
Yeah, like is that a captured one, or is it just, the further you get away, the weaker the gravity is. Maybe at some point you cross a barrier, which is, we don't do that. We don't do resonances out here. We just orbit.
Yeah, because this is one of the most pristine systems that we know exists, in the sense that we know it's not been disrupted by anything. We know that the star's about 1 billion years old. So it's basically the star was born, it had its planets, and this is where it's still at. It's, there's not been any major catastrophic events that have tidally disrupted the planetary system, because otherwise they wouldn't be in this lovely pattern anymore. So it's I think one of the scientists called it a fossil. in that sense. It's a pristine fossil of what a solar system can do.
All right. Let's pull this all back around then. We have this amazing system, this fossilized system, right? What does that do for us? Like from an astronomical point of view, Emily, what's the excitement in this? Where does it get us?
Yes, well, astronomers often get accused of being stamp collectors.
Great, we found a system
Not that we don't like
this.
stamp collectors, but yeah, I mean, it's true. We're quite interested in the variety of stuff that you can find in the universe. And is this just therefore another rare stamp? Is this just a curiosity that we can put in a little cabinet and say, hey, there's a cute little one over here that we can come and look
once
at?
the excitement of that particular stamp dies down, goes into the album, and we never talk of it again. Is it one of those?
Well, I think we've already implied that it's not, because we've already said this is James Webb's favorite type of system to be going and looking at.
This is one of the big reasons why James Webb's up there.
Exactly. And we're excited to find out more about these sub-Neptunes, and that in its own, I think, is just exciting. Of course, we don't need the resonance element of that to be true, right?
No, that's just a happy bystander fact.
No, but the resonance does tell us at least that these aren't things like captured planets. This isn't a system that's been messed around with.
Right, that its fossil status allows you to go, all right, look, if you want information about planets that have been there undisturbed for a really long time, this one. And we know it's this one because.
Yeah, they formed together, they've evolved together.
Yeah, that makes sense.
And with the star as well. So you've got all of that information to put together. And that all contributes to our understanding of how planetary systems form, because it's harder than it seems to put together a really good picture of how to form a planetary system. We still have no idea what happened in the early parts of our own solar system's evolution. Why have we ended up in this strange sort of configuration we have? Our 4 inner planets, the rocky planets, fine. They basically have done what they've done. They've stayed there. But Jupiter, Saturn, and Uranus and Neptune, there's so many possibilities of what could have happened to get them into this kind of strange situation that they're in now. Why is Jupiter so big, and why is it there? And maybe there's been some tampering, because it almost looks like Uranus and Neptune have switched places at some point in the past.
You astronomers often sound just so confident and sort of reassuring. Of course we understand all of this stuff. It's kind of fun to hear you talk about it. We don't know. No idea about that one.
No. But that's the excitement, right? I mean, our solar system is nowhere near this kind of endpoint fossilized status. We're still very much young and evolving, and you can look at it both ways. You can use this to look at the early stages of how did we get to where we are today, but also what is the future of our solar system, and are we going to end up as a resonant a resonant octuplet of planets later on down the line.
Yes, are we glimpsing our own future here? And what song is our solar system going to play? Emily, after a protracted update from a couple of past episodes, we got into what to me is just a fascinating story of this fossilized planetary system far, far away that's just playing some beautiful, beautiful music. It's wild stuff. I love this. This is great.
Yeah, coming from a field where we have to often say, look, yes, I can turn my star into music. Do you want to hear it? Probably not, because it sounds awful.
When we say music, but in this case, it really is kind of musical. And as you mentioned before, this is a podcast. This is an audio medium. It's not very often that we get to say, yeah, this is the best medium for this story. But It really, really is.
Oh, 100%.
Yeah, really nice. Listen, if people wanted to get in contact with us and, for example, submit any lyrics that they've written to go along with this planetary music, that would be awesome. Emily, how do people contact us here on the show?
So you might have to give us the tempo for your lyrics, but you can pop them all in our lovely web form, which is attached to the syzygy.fm website.
Yes, indeed. Head along there and you can find all sorts of other stuff, like every other past episode, including the ones that we've just given a couple of updates on, going all the way back to episode 0. But there are other ways that people can get in contact with us as well. We are on some of the socials. We're on all of the sort of, much as I hate to say it, the meta-related ones. We're on the Facebook. And do you know what I've found out? People can just go to facebook.com/Syzygy podcast.
Oh,
Yeah.
This is
There you go.
taking us a while to figure that one out.
Who knew?
After how many episodes?
And you can go to Instagram, and we're at SyzygyPod, or you can go to Threads, and we're at SyzygyPod. Go and find us. We put up updates about the different episodes as they're released, and any other bits and pieces that come along that take our fancy, and you can get in contact with us through those. If you want to support the show, the best thing you can do is to tell everyone you know that there's this really cool podcast, and it's called Syzygy, and you should go and tune in if you're at all interested in the universe and our place in it. The other thing you can do is throw a couple of dollars, a couple of quid our way over at patreon.com/SyzygyPod to keep the electrons flowing through the podcast and help us to continue to do the things that we do every roughly week or so. Speaking of which, Emily, might catch up with you in a week.
Yes.
At most, a couple of weeks. Until then, see you later, everybody. Catch you soon.
See you later.
Bye-bye.